Now let's look at the limit comparison test. The limit comparison test tells us that if both a and b are positive, and the limit as n approaches infinity of a over b is equal to some number L, and L is finite and positive, then either both series converge or they both diverge. So what do we have to show on this? We have to show first that our sequences are positive, that there is a limit that is positive and finite. And then we can conclude that they either both series converge or diverge. So let me look at this limit comparison test. Let me look at this right here using the limit comparison test. The sum as n goes from 1 to infinity of 1 over a n plus b. Now, what does this kind of look like? It kind of looks like the sum as n goes from 1 to infinity of 1 over n. Now I know this diverges. Now a sub n, 1 over a sub n plus b is indeed positive. 1 over b sub n is positive. So now let me look at the limit as n approaches infinity. Now you notice it doesn't really matter which one I put in the numerator, of 1 over n divided by 1 over an plus b. Well, this is the limit as n approaches infinity of an plus b over n, or a. Now I assumed a is positive. So indeed, L is equal to a is positive and finite. Therefore, the sum as n goes from 1 to infinity of 1 over an plus b diverges just as the harmonic series did. Now let's look at this one. What you want to do is back up and just sort of look at the highest power. This is positive, and let me look at the sum as n equals 1 to infinity of, I'm going to ignore this term, and this is n to the minus 3 halves. So let me look at this right here. And I know this is a convergent, B-E-R-G-E-S, because it's a p-series. So let me compare these two. Let me look at the limit as n approaches infinity of the square root of n divided by n squared plus 1 divided by n to the minus 3 halves. Now this is an awkward way to write this. So this is a limit as n approaches infinity of n squared divided by n squared plus 1, which is 1. So the limit is 1, it's positive and finite. Therefore, the sum as n goes from 1 to infinity of the square root of n over n squared plus 1 converges because the p-series converged by the limit comparison test. So let me just give you a few hints. If you're looking at something like 1 over this polynomial, look at the highest power of the polynomial. All right? When you do this limit, you're going to find that both series converge. When you've got this square root in here, just ignore everything else except the square root and compare it to 1 over the square root of n, which diverges. So both of these series will diverge. Now what do you do if you have two polynomials? Just look at the highest power of your polynomials, and this is going to look like 1 over n cubed. So when you compare it to 1 over n cubed, you see this converges, therefore this converges as well. Now finally, what do you do when you have something ugly, really ugly? As n goes from 1 to infinity of n 2 to the n over 4n cubed. Now let's look at the sum as n goes from 1 to infinity of 2 to the n divided by n. I'm going to cancel one of those, so that's just squared. Now this diverges. Okay. So let's look at the n-term test. The limit as n approaches infinity of n 2 to the n divided by 4n cubed plus 1 divided by 2 to the n divided by n squared. Oops. Now, yes, it would have been much easier to write it this way. The limit as n approaches infinity of n 2 to the n divided by 4n cubed plus 1 times, let's see, that's going to be n squared divided by 2 to the n. And we wind up with, let's see, I've got n cubed, 2 to the n. The 2 to the n's are going to cancel. So this is the limit as n approaches infinity. I'm going to go and cancel those, of n cubed divided by 4n cubed plus 1, which is 1/4. This is positive, finite. So now what function did I compare it to? I compared it to a function that diverges. Therefore, the sum as n goes from 1 to infinity of n 2 to the n divided by 4n cubed plus 1 diverges by limit comparison test.